All right, so let's work on some practice problems from our textbook, starting with section 7.3 here, where we're going to be assessing normality. So for this first question here, question 4, we're going to use the results in this table to first draw a normality plot, then determine the linear correlation between our observed values in this column and our expected z-scores here. And then lastly, determine the critical value to assess the normality of the data. So for part A, we're going to draw a normality plot. So we're going to plot our observed values versus our normal scores. And so I have our plane set up here. So on our x-axis or horizontal axis is going to be our observed values versus our expected z-scores. So that's what's going to go in this vertical axis here. All right, now let's just label these guys. For our observed values here, notice our range is from 77 all the way up to 120 here. So let's start with 70 and then we'll just increase in increments of 10. All right, and then doing the same thing for our y-axis or vertical axis here, we need to plot these guys. So maybe let's start at -2 down here and then work our way up to +2. So we're going to do -2 and let's increase in increments of zero point 0.5. All right, so from here, we're just going to plot these guys. So for example, for our first point, it's going to be our observed value is 77. So we're going to be right around here on our vertical axis. And then in the horizontal direction here, our expected z-score is going to be -1.48. So approximately -1.5, just below it. So our first point is going to be somewhere around here. Our next point is our observed value is going to be 80, and our expected z-score is going to be -0.92. So we're going to go 80 up to -0.92. So that'll be just above -1 here, since -0.92 is bigger than -1. So we're going to repeat this process here, and I'll fill in the rest of these points. Okay, so filling in the rest of these points here, this is our normality plot for part A. Now for part B, we want to determine the linear correlation between the observed values and the expected z-scores. And so we know how to find this from section 4.1. We have the formula here. This is just our linear correlation coefficient. So we need to find these values, plug them into this formula, and see what we get. So we're treating x as our observed values and then y as our expected z-scores. So the mean of our observed values, I'm just going to give this to you guys because we know exactly how to find this. We're just going to take the sum of all of our observed values and then divide by the total number of values. So when we do that, we're going to get that the mean of this guy is 99, and then the standard deviation is going to be approximately 14.415. Now doing the same thing for our expected z-scores, we're going to get that the mean is 0 and our standard deviation is approximately 0.713. Now what we want to do is find the sum of the products of these guys. Okay, so for each observed value, we're going to plug them into this formula here. So first we plug in 77, see what this is. Then we plug in -1.48 for this y, see what that is. Take the product of these guys, and then we're going to do that for each of these values here, and then take the sum of them. So when we do that, we're going to get So finding this value here, we're going to get that this is approximately 7.844. So we're going to plug this directly into this formula up here. In our numerator, this is going to be 7.844. And in our denominator, this is going to be n minus 1, so the number of observations here, minus 1. Going back up to this table, we have 9 of them. So in our denominator, we're going to get 8. So this is going to be approximately 0.98. Now, lastly, for part C, put that there, we want to determine the critical value in this table here to assess the normality of the data. So in this case, our critical value is going to be 0.912 since our sample size is 9. So since we have our correlation coefficient R is greater than, this is our critical value, there's going to be evidence that this sample data comes from a population that is normally distributed. So this is purely just from this R value. So we'll write that here. So because of this, there is evidence that this data comes from a population, which I'm going to abbreviate as that is normally distributed. All right, and that's how we would do a problem like this. Okay, so for this next example, we're told that a random sample of college students aged 18 to 24 years was obtained, and the number of hours of television watched in a typical week was recorded. So we have this data in this table here, and we're going to use it to answer the following questions. So for part A, we're asked to draw a normality plot to determine if the data could have come from a normal distribution. Now, in the interest of time, I've pasted the normality plot here for us. We should all know how to draw a scatter plot. So we have this here for us, and we're going to use it to determine if the data could have come from a normal distribution. Now, notice this plot is roughly linear, and we don't have any crazy outliers really, so we can assume that the sample could have come from a population that is normally distributed. So we'll write that here. Um, so the sample could have come from a population that is normally distributed, since the plot here on the left is roughly linear and we don't have any crazy outliers here. So that's it for part A. For part B, we want to determine the mean and standard deviation of the sample data. Okay, so we know that the mean given by X bar here is going to be the sum of all of our values divided by the number of values that we have. Okay? So we're going to take the sum of all of the values in this table here, which I'm going to give to us. That is going to be 522.6. And then the number of values that we have in this table is 25. So plugging this information in to this formula, this is going to be approximately 20.9 hours. So that's going to be the mean amount of time that is spent watching television. Now, to find the standard deviation of this sample data, we're going to plug this into our standard deviation formula, which looks like this here. So we have all of this in our numerator, and our denominator, we're going to have n minus 1, and this whole thing is under a square root. So we're going to plug in this information here. And so I'm going to give us the sum of our x values squared. This is going to be 13,578.84. Okay, so we have all of the other information that we can just plug directly into this formula here. So this first value is going to be this. Then we're going to subtract out the sum of our x values and then square it. And then divide that by the number of observations, so 25, and this is all over n minus 1 observations, so 24. And then lastly, we have to square root whatever number we get there. Doing so, we're going to get this is approximately 10.52 hours. So that is going to be the standard deviation for the sample data. Now for part C, we want to use the sample mean and standard deviation as estimates for the population mean and population standard deviation, and draw a graph of a normal model for the distribution of weekly hours of TV watch. So we know how to do this from the last video. In the middle here is going to be our mean, which we found to be 20.90 from part B. Now our inflection points here is going to be our mean minus our standard deviation and our mean plus one standard deviation. So this is going to be our first point to the left of our mean. So one standard deviation away from our mean gives us 10.38. And then one standard deviation to the right of our mean is going to give us 31.42. All right, so we're going to draw our curve here, which is going to look something like this. So this is our mean, and these are our inflection points there. Okay, so for part D here, we want to use the normal model from part C to find the probability that a college student aged 18 to 24 years, selected at random, watches between 20 and 35 hours of TV each week. Okay, so in this case, we are going to transform our random variable x into our standard normal random variable z. So we have our lowercase x, we're going to call sub 1 is 20, and our lowercase x sub 2 is going to be 35. So we need to transform both of these x values into z-scores, just like we saw in the last video in, I think, section 7.2. So we're going to call this z sub 1. This is going to be x sub 1 minus our mean divided by our standard deviation. This is going to be 20 minus our mean of 20.9 divided by our standard deviation. This will give us, and this is approximately negative 0.09. And then our second z-score is going to be x sub 2, again, minus our mean divided by our standard deviation. This is going to give us approximately 1.34. Okay, so just like we saw in the last video, let's do our normal curve again. So let's say this is 20 and this is 35 hours of TV watch. We want to find everything in this interval here. Okay, so the z-scores, let's draw our curve here, corresponding to these x values we found to be negative 0.09 and 1.34. So if we look at table 5, we're going to find the area under the curve to the left of these values. So the area to the left of this guy, negative 0.09, is going to be 0.4641. So just looking at table 5, and then the area to the left of our z-score of 1.34 is going to be all of this, and that is going to be 0.9099. So if we want to find everything in between these guys in this interval here, we're going to have to take the area in green here under this curve and subtract out everything in blue. Doing that, we're going to be left with everything in green. So the probability that a college student is going to watch between 20 and 35 hours of TV is going to be given by this area in green, this 0.9099, subtracting out the area in blue, 0.4641, which is going to give us 0.4458. So this is the probability that a randomly selected college student watches between 20 and 35 hours of TV each week. So this brings us to section 7.4, where we're looking at the normal approximation to the binomial probability distribution. So for question 10 here, we're going to be given a discrete random variable. We want to assume the probability of this random variable will be approximated using the normal distribution. So we want to describe the area under the normal curve that will be computed. So in this scenario, we want to find the probability that the number of tornadoes that occur in the month of May is between 30 and 40 inclusive. So we're including the values of 30 and 40. Now, before answering this, let's look at this table that is from our textbook here. So if we want to find the exact probability using the binomial probability distribution, so the probability of some value A occurring, in order to approximate it using the normal distribution, we want to find the area under the normal curve in this region here. So in order to do that, we're going to add, or we're going to subtract 0.5 to this a value. That'll kind of be like our lower like bound here. And then we're going to add 0.5 to this value. That'll kind of be our upper bound. And we want to find the area in this region. Okay, so by doing this, by adding and subtracting this 0.5 from our value A, this is serving kind of as a correction for continuity because when we're doing this, we're using a continuous density function, but we're approximating the probability of a discrete random variable. So this adding and subtracting of this 0.5 quantity is kind of, it serves as that correction, kind of gives us some wiggle room here since we're approximating this. Now, in this case, going back to this example, we want to find the probability that the number of tornadoes that occur in the month of May is between 30 and 40. So we're looking at this last case here, the probability that the number lies between 30 and 40. So A is 30 in this case and B is 40. So in order to approximate that using the normal probability or the normal approximation, we are going to be using this guy. So we want to find the area under the normal curve in this region. So we're going to subtract 0.5 from our A value, which was 30, and then add it to our B value, which is 40. So let's write that up here. So we're going to approximate the probability that the number of tornadoes that occur in the month of May is between 30 and 40 by computing the area under the normal curve between, so we're going to subtract 0.5 from our A value. So between the 29.5 value and we're adding 0.5 to our B value. So 40.5. Okay. So that's it for that question. Let's look at question 24 here. So, according to a study done by Nick Wilson of Ottawa University, the probability a randomly selected individual will not cover their mouth when sneezing is given by 0.267. So suppose you sit on a bench in a mall and observe 300 randomly selected individuals' habits as they sneeze. We're going to use the normal approximation to the binomial to approximate the probability that of the 300 randomly observed individuals, exactly 100 do not cover their mouth when sneezing, and fewer than 75 do not cover their mouth. Okay, so let's write down some stuff that we know. We know in this case that the probability that a randomly selected individual will not cover their mouth when sneezing is given by p here, and that's going to be 0.267. We also know that our sample size is going to be 300. We're observing 300 randomly selected individuals. Now, we also know that this value here, this n times p times 1 minus p, we know that this needs to be greater than or equal to 10. So plugging in these values here, we're actually going to get that this is 58.7133, which is in fact greater than or equal to 10. So the normal approximation to the binomial distribution can be used. And we also know that the mean in this case is going to be n times p, which is going to give us 300 times this probability. Okay, so that's the formula that we use for the mean in this case. Now, the formula for the standard deviation in this case is going to be given by the square root of n times p times 1 minus p here. So the square root of this value. All right, so this is going to give us, if we plug everything in there, this is going to give us approximately 7.662. So with this information, we can now answer parts A and B here. So first for part A, we want to find the probability that exactly 100 people do not cover their mouth when sneezing of a random sample of 300 individuals. So let's put this here for part A. We want to find the probability of 100. And we know that we are going to approximate this using the normal distribution. So going back to this table here, if we're trying to find the exact value probability of A, and in our case 100, then we're going to find this probability here. So we're going to do 100 minus 0.5 and 100 plus 0.5. So this would be approximately equal to this. And we know from the last video, what we're going to do is we're going to transform these x values into z-scores. So we're going to do so a little bit differently than we saw in the last video. Instead of getting the individual z-scores, which I called z1 and z2, and then kind of drawing the area and going that route, instead I'm going to kind of just leave it in this format here. So what I mean is our first x value that we're transforming into a z-score is 99.5. And we know we're going to do that by plugging it into this formula where we take that x value, we subtract out the mean and divide by our standard deviation. And then we're going to do the same thing for our other x value. We're going to subtract the mean and divide by our standard deviation. Okay. Doing so, we're going to get z-scores of 2.53 and 2.66. Okay, so what's happening here is we transform these x values into these z-scores. So now we need to find the area under the curve corresponding to these z-scores. So let's see if we have room to draw our normal curve here. So we're looking at the area in between 99.5 and 100.5. So we want to find everything in here. All right. So in order to do that, we know that we're going to need to find the area under the curve corresponding to this guy. So this z-score, this 2.66, and the area corresponding to this guy, so this z-score. Then what we do is we take this entire area and then we subtract out the area here, leaving us everything in between. So the area corresponding to this z-score, this 2.66, is the bigger area. So we're going to start with this one. So 2.66 is going to give us this 0.9961. Okay, so that's the area under the curve corresponding to 100.5 or the z-score of 2.66, just to really emphasize that. And then the area under the curve corresponding to 2.53 is going to be given by 0.9943. All right, so subtracting these guys, we're going to get that the probability is 0.0018. The probability that exactly 100 individuals out of the 300 do not cover their mouth when sneezing. All right, now let's do part B here. We want to find the probability that fewer than 75 do not cover their mouth. So for part B, we're trying to find the probability that X is less than 75. Now, this one is a little different. If you notice going back to this table, because we're again wanting to use we're trying to approximate this using the normal distribution. So going back to this table here, we might want to use this one, the probability that x is less than or equal to some value a, but remember we don't have inclusivity in this case. We're not looking at the probability that x is less than or equal to 75, so we can't use this, not yet. What we can do in this case is we can transform this statement into an inclusivity statement. And we can do so by saying this here, the probability that x is less than or equal to 74. Okay, because these guys are equivalent in this case here. The probability that something's less than 75 is going to be the same thing that something is less than or equal to 74 in this case. And this is because we're dealing with binomial random variables, so the values of the random variables must be whole numbers. So in this instance, with our binomial random variables, these guys are equal. So now that we've transformed this statement into an inclusivity statement where the probability is less than, or the probability that x is less than or equal to some value, in this case 74, now we can use this and we can use this. So this can be approximated by the probability that x is going to be less than or equal to, in our case, 74 plus 0.5. So less than or equal to 74.5. So from here, we're just going to do the same thing that we saw in part A. This is going to be the same thing as transforming this into our z-scores. So 74.5 minus our mean divided by our standard deviation. We're going to get that x is less than or equal to, so taking this, oh, sorry, taking this difference and then dividing by our standard deviation, we're going to get negative 0.73. So this is our z-score, and then going to our table, we need to find the value of negative 0.73. That'll give us this probability, and that is the area under the normal curve, and that is 0.2327. And apologies, I just realized that my notation is slightly off. When we are transforming our random variable x into these z-scores, it's actually standard practice to switch this into our variable z instead. So we'll have that for that one. And then for part B, same here. Once we transform our uh, x's into z-scores, we're going to use our standard random variable z in this case. All right, and then something else to note here for this problem, that notice for part B, we were asked what's the probability that fewer than 75 do not cover their mouth? If we were trying to find the probability that more more than 75 do not, this is going to be the same thing as the probability that x is greater than 75. And just like we saw in part B, we run into this issue again. We might want to use this here, but we don't have inclusivity in the statement that we're looking at. So what we'll do in this case is we're going to rewrite this in the same way that we did for part B here. We're looking at the probability that x is greater than 75. This is going to be the same thing as the probability that x is greater than or equal to 76. Okay? We're looking at values greater than this. We are looking at values greater than 76 and including 76, since 76 is greater than 75. So from this point, now we have an inclusivity statement, and we can use these guys. So we're going to approximate this using the probability that x is going to be greater than or equal to a minus 0.5. So in this case, 76 minus 0.5, which gives us 75.5. Now from here, we're not quite done yet. If we're trying to find this probability here, notice we're looking at everything shaded in blue in this region. And if we do the process that we just saw, where we find our z-scores and the corresponding area under the curve, remember that area is everything to the left of whatever that z-score is. So in this case, we have to take this entire thing, which is 1, and then subtract out the area that we get by finding the z-scores. When we do that, we're left with what's under here. So in order to find this probability, what we do is we would take 1 minus the probability that x is less than or equal to the 75.5. And so that's how we would solve this problem if we were asked the probability that more than 75 people do not cover their mouths when sneezing. This brings us to section 8.1, where we're looking at the distribution of the sample mean. So for question 16 here, a simple random sample of size 36 is obtained from a population with mean 64 and standard deviation 18. So for part A, we want to describe the sampling distribution of the sample mean here. So our sample mean is given by this X bar here, just to make that clear. Okay, so we note that since our mean is 64 and our standard deviation is given by this here, the expected value of our sample mean, which is denoted with this mu sub x bar here. So that's going to be the expected value of our sample mean. It's going to be equal to our population mean mu. And this is because when you take a bunch of samples and calculate their means, those means will, on average, equal the population mean. So the more samples you take, the closer that the mean will be equal to the population mean. And then our standard deviation, or the expected value of our standard deviation of the sample mean, is going to be equal to the standard deviation divided by the square root of the number of samples that we have. So this is going to be given by 18 divided by the square root of 36, which gives us 18 over 6, which gives us a standard deviation of 3. Okay. We don't have that the population is normally distributed. We're not told that, but note here, we have a sample size of 36. So this is actually greater than or equal to our sample size of 30. So in this case, we can use the central limit theorem So the central limit theorem says this the sampling distribution. So the sampling distribution of our sample mean is approximately normal. All right, so that is the little description of our sampling distribution of the sample mean. Now for part B of this problem, we want to find the probability that the sample mean is going to be less than 62.6. So we want to find the probability the sample mean is less than 62.6. And we know how to do this. We are going to transform this x value into a z-score. So we want to find the probability that z is going to be less than this z-score, which we find by subtracting our sample mean and then dividing by the standard deviation. All right, doing so, we're going to get that our z-score is negative 0.47. And then looking at table 5, this is going to be 0.3192. So this means if we take 100 simple random samples of size 36, in this case, with a population or from a population with mean 64 and standard deviation of 18, then roughly 32 of the samples will result in a mean that is less than the 62.6, because this is about 32%. So 32 out of 100. So we'll write that here. If we take 100 simple random samples of size, in this case 36, with the given mean and standard deviation, about 32 of the samples will result in a mean that is less than that 62.6. Now let's do something similar for part C. Now we want to find the probability that the sample mean is going to be greater than or equal to 68.7. So we're going to do something similar. This probability we can find by using z-scores. So the probability that the sample mean is greater than or equal to that is equal to the probability that z is going to be greater than or equal to the z-score that we get by transforming this x value here. This is going to give us 1.57. So the corresponding z-score is 1.57. And remember, the z-score, or if we look at this z-score on table 5, we're going to get the area under our normal curve. But remember, it's the area to the left of this value, the 68.7. So in order to find the area to the right of this value, we're looking at all the values that are greater than this z-score. We're going to have to take this as 1 minus the probability that z is less than this 1.57. So just like we saw in the last video and in the last several examples, this is going to give us, looking at table 5, the area corresponding to this z-score is going to be 0.9418. So we're going to get that this probability is 0.0582. So this means if we take 100 simple random samples with this information, then about 6 of the samples will result in a mean that is greater than or equal to the 68.7. And lastly, we're going to do the same thing here. We want to find the probability that the sample mean lies between these two values here. Again, we are going to use our z-scores. So this is going to be the probability, and we're transforming the 59.8 into a z-score. And then the 65.9 into a z-score. So just like we've been seeing for the last several examples, we're going to get the corresponding z-score for 59.8 is negative 1.4, and then the one corresponding to 65.9 is 0.63. Now remember, we're trying to find the area between these values here. So we're going to take the area to the left of this guy and subtract out the area to the left of this guy, giving us what's left over in between. So the z-score corresponding, or sorry, the area under the curve corresponding to this z-score from table 5 is going to be 0.7357, and the one corresponding to negative 1.4 from table 5 is this here. So the probability that our sample mean is going to lie in between these guys is 0.6549. So this means, again, if we take 100 simple random samples, we're given this information, so size 36, mean 64, and standard deviation 18, then about 65 of the samples will result in a mean that is in between 59.8 and 65.9. So for question 28 of section 8.1, suppose that cars arrive at Burger King's drive-thru at the rate of 20 cars every hour between noon and 1 p.m. So a random sample of 41-hour time periods between noon and 1 p.m. is selected and has 22.1 as the mean number of cars arriving. So for part A, why is the sampling distribution of our sample mean approximately normal? So similar to what we saw in the last example, first, notice that our sample size is large. In this case, our sample size is 40, which is greater than or equal to 30. And from the central limit theorem, as the sample size increases, the sampling distribution of the mean becomes more normal. So we'll say that here. Um, so the sampling distribution of our sample mean is approximately normal due to the central limit theorem, which I'm going to abbreviate with this. Um, as the sample size increases, we know that the sampling distribution of the mean becomes more normal. Becomes more normal. Okay. For part B, this is also similar to the last problem we saw. What is the mean and standard deviation of the sampling distribution, assuming that our population mean is 20 and our population standard deviation is the square root of 20? So we know in this case that the mean, given denoted by this guy here, is going to be equal to our population mean, which is 20. And then our sample standard deviation here is going to be given by the standard deviation of our population divided by the square root of the number of samples that we have. So this is going to be the square root of 20 divided by the square root of 40. Now we can simplify this. This is going to be the same thing as the square root of 1/2, which is going to give us approximately 0.707. All right. Now this is just because, I guess maybe let's make this more clear. This is the same thing as the square root of 20 over 40. And we know that 20 divided by 40 is just 1/2, so that's why we get the square root of 1/2. All right. And then for part C, what is the probability that a simple random sample of 41-hour time periods results in a mean of at least 22.1 cars? And then is this result normal or unusual? What might we conclude? So let's set this up here. We want to find the probability that our sample mean is going to be greater than or equal to 22.1. Again, we know how to do this. We know that we want to convert this z value or this x value of 22.1 into a z-score. So changing this to a z there, subtracting out our mean and dividing by our sample standard deviation. Now we have to be careful. In this case, it's not just going to be this sigma here. It's actually going to be this guy. So the 0.707. All right. So we're going to get The z-score is 2.97. And again, we know that the area under the curve corresponding to this z-score is going to be everything to the left of that guy. So in order to get everything that's greater than or everything to the right of this z-score, we're going to take 1 minus the area corresponding to the z-score of 2.97, which we can find from table 5 as 0.9985. So this is going to give us 0.0015. So that is the probability that a simple random sample of 40 1-hour time periods results in a mean of at least 22.1 cars. So this means if we take 1,000 simple random samples of the same size and is equal to 40 1-hour time periods, then about 2 of the samples will result in a mean of at least 22.1 cars arriving at the drive-through. Now, this result is unusual. We might conclude that business has increased and that the rate of arrival is maybe now greater than the 20 cars per hour that we saw before between the hours of 12 and 1 p.m. This brings us to section 8.2, where now we're looking at the distribution of the sample proportion. So for question 12 here, a simple random sample of size 200 is obtained from a population whose size is 25,000 and whose population proportion with a specified characteristic is 0.65. So first we want to describe the sampling distribution of our sample proportion, this p hat here. So first thing to note is that our sample size in this case is 200. Now this is going to be less than the 5% of our population size. So this is less than 5% of our population size, which we find by multiplying our population size by 5% or 0.05. This gives us 1250. So 5% of our population is 1250. So clearly the sample size of 200 is less than that. And secondly, if we take this quantity here, plugging in our known values, this is going to be 200 times 0.65 times 1 minus 0.65, so 0.35, which gives us a 45.5, which is in fact greater than or equal to 10. So this means that the distribution of our sample proportion, that p hat, is approximately normal. And the mean, which is denoted with mu sub p hat here, is going to be equal to this population proportion given in this problem, which is 0.65. And then the standard deviation of our sample proportion, denoted like this here, is going to be given by this. So let's plug in our known values. This is going to be p times 1 minus p. Oh, 1 minus p divided by our sample size, and then we're going to take the square root of that, which is going to give us approximately 0.034. All right, so that's what the sampling distribution of our sample proportion looks like. For part B, what is the probability of obtaining 136 or more individuals with the characteristic? That is, what is this probability here? So we're going to proceed just like we've seen in the last several examples here. We're just trying to find the probability that this sample proportion here is greater than or equal to 0.68. So just like we saw in the last several examples, what we're going to do is transform this 0.68 into a z-score. So we want to find the probability that this guy's going to be greater than or equal to the corresponding z-score, which we find by subtracting out our mean and then dividing by our standard deviation. Doing so, we're going to get that the corresponding z-score for this guy is 0.89. But remember, we want to find the area under the curve for this guy, for this v-score. It's going to be the area to the left of this. So in order to find everything to the right of that, we're going to take 1 minus this probability. And looking at our table 5, the area under the curve corresponding to this z-score is going to give us 0.8133, which is 0.1867. Okay. So this means, rounding this up, about 19 out of 100 random samples of this size n is equal to 200 will result in 136 or more individuals with that characteristic. Okay. So I'll write that blurb on the side when I upload the solutions. For part C, what is the probability of obtaining 118 or fewer individuals with this characteristic? So we're looking at this guy here. So we're going to do the same thing here. We need to transform the 0.59 into a z-score. The corresponding z-score is going to give us negative 1.78. And then for this one, we know that the area under the curve corresponding to this z-score is going to be everything to the left of the sky, which is exactly what we're looking for. So this is just going to be 0.0375. So roughly, if we round this up, about 4 out of 100 random samples will result in 118 or less people with this characteristic. Now for this next question, a researcher studying ADHD among teenagers obtains a simple random sample of 100 teenagers and asks them whether or not they've ever been prescribed medication for ADHD. Now, we want to say that the distribution of our sample proportion of teenagers who respond no is approximately normal. And in order to do that, we want to find how many more teenagers the researcher needs for the sample if our population proportion is 90% and if our population proportion is 95%. So for part A, the first thing that we know is that our population proportion is 90% or zero point 0.9. Now, in order to say that this sampling distribution is approximately normal, we need two things. We need this quantity to be greater than or equal to 10, and we need our sample size n, which is what we're trying to find. We need this one to be less than or equal to 5% of our population, capital N. Now, we don't know what our population is, so we're just going to assume that this quantity holds. What we need to do is make sure that this one does as well. So we already know what P is. In this case, it's 0.9. So we're just going to plug this into this inequality here and then simplify. So simplifying this, we're going to get 0.9 times 0.1 times n. Doing that, we're going to get 0.09 times n is greater than or equal to 10. So from here, we can just solve for n by dividing by 0.09 on both sides of this inequality here. Doing so, we're going to get that n is greater than or equal to 111.11. So we need a sample size of 112. So we need sample size of 112, or remember in our problem here, a researcher studying ADHD among teenagers obtains a simple random sample of 100 teenagers. So we already have that. So in other words, we just need 12 more teenagers. All right. And then for part B, in this case, P is given by 0.95. So we're going to do the same thing here. We want to make sure that this inequality here is satisfied. So we want to make sure that n times p, which is 0.95 in this case, times 1 minus 0.95 is greater than or equal to 10. All right, so this is going to give us this here on the left-hand side of our inequality. Simplifying a little further, we're going to get this here. And then lastly, if we want to divide by 0.0475 on both sides to get our variable n, which is the unknown value, completely isolated. Doing that, we're going to end up with this here. So we would need a sample of 211 teenagers. So of 211, or 111 more teenagers, since we started off with a sample size of 100. All right, so in section 9.1, we're estimating the value of a parameter using confidence intervals. So for question 26 here, we want to figure out relative to other nations how fourth graders in US rank in terms of reading and math ability. So are they in the top or bottom 50%? Now, in a survey of 700 randomly sampled registered voters in the US, 258 correctly answered that fourth graders are in the top 50%. So for part A, we want to obtain a point estimate for the population proportion of US registered voters who believe fourth graders rank in the top 50%. So we need to find the point estimate for the population proportion. Now that is given by p hat here, and this is going to be X over N, where X is the number of individuals in the sample with a specified characteristic. And in this case, that's the registered voters who believe fourth graders rank in the top 50%. And then we know that N is our sample size. So in this case, our point estimate, the population or the sample proportion, this P hat, is going to be 258 out of 700. This is going to be approximately 0.369. Pretty simple for that one. Let's look at part B here. We want to verify that the requirement for constructing a confidence interval about P are satisfied. So the sample is a simple random sample. We need to make sure that this quantity is greater than or equal to 10. So let's plug in our known values. We have 700 for N. We just found P to be approximately 0.369. This is going to give us approximately 162.99, which is in fact greater than or equal to 10. We can also assume that the sample is less than 5% of the population, since relative to the entire population, 700 randomly sampled registered voters is definitely less than 5% of the population of registered voters. Okay. Then for part C, we're going to construct a 95% confidence interval for the population proportion of US registered voters who answered correctly. So we're going to construct our first confidence interval. As you can see, I have our lower and upper bound here. So what we need to do is find the information for these formulas and then plug it directly into these formulas. So first things first, we already know what our p hat is. We already know what n is. So the only thing we really need to find is this z sub alpha over 2. Now, we want a 95% confidence interval. So this means alpha is going to be equal to 1 minus 0.95, which is going to give us 0.05. So z of alpha over 2 is the same thing as 0.05 divided by 2, which gives us 0.025. Now, I pasted table 5b here from the appendix. This is just a table of some common critical values for z of alpha over 2. So looking at 95% confidence for z of alpha over 2, that's going to give us a critical value of 1.96. So z of alpha over 2 is 1.96. So we can just plug in this known information into our lower and upper bounds. So for our lower bound, we're going to have p hat. Let me just move this and we can insert this directly into the formula that we have here. So p hat is 0.369. We're going to minus our critical value and then multiply it by the square root of this guy. All right, I'm going to take the square root of this. This is going to give us 0.333. And we're going to do the same thing for our upper bound. We're going to have our p hat value. We're going to add our critical value and multiply it by the square root of this guy. Doing so, this is going to give us 0.405. Okay, so that is our lower and upper bounds. And for part D, we want to interpret this interval. So we constructed a 95% confidence interval. So this means we are 95% confident that the proportion of registered voters in the US who answered correctly, so they answered that fourth graders are in the top 50%, is between 0.333 and 0.405. Now for this next problem, we're trying to determine the sample size required to obtain a certain confidence interval. So for question 36 here, an urban economist wishes to establish the proportion of Americans who own their own homes. What size sample should be obtained if he wishes the estimate to be within 0.02 with a 90% confidence? If he uses 2010 estimate of 0.669 obtained from the Census Bureau. Okay, so let's break this down here. We know that the formula for a sample size is going to be given by this here, where p hats are going to be prior estimates. We know that this is going to be our critical value, and then E is going to be our margin of error. So, first of all, we are looking at a 90% confidence. So, this means alpha is going to be 1 minus 0.9, which is going to be 0.10. This tells us that our critical value is going to correspond to just 0.10 divided by 2. And this critical value, actually scroll back up to this table here, is going to be 1.645. Okay. For this p hat here, this is going to be our prior estimate of p, and we're going to use this 0.669. And then lastly, our margin of error was given here to be 0.02. So let's plug all of this information in. We're going to find we're going to have 0.669 times 1 minus 0.669. We're going to multiply this by our critical value divided by our margin of error, and then we're going to square that. So doing so, plugging this directly into a calculator, we're going to get this here. Okay, so our sample size needed for this certain scenario is going to be 1,499. Now, for part B, we want to figure out the sample size if he did not use any prior estimates. So in this case, we have another formula for this. Our sample size is then just going to be given by this here. So we still need that critical value and our margin of error, but we don't have any prior estimates. Scoring that, this is going to give us 1,692 for our sample size for this scenario. All right, so in section 9.2, we are going to be estimating a population mean. We are going to look at the t-distribution, determining t-values, and then constructing and interpreting a confidence interval for the population mean. So that's how we're going to estimate it. So let's look at question 28 here. So how much time do Americans spend eating or drinking? Suppose for a random sample of 1,001 Americans age 15 or older, the mean amount of time spending eating or drinking per day is 1.22 hours with a standard deviation of 0.65 hours. So for part A of this question, we're told that a histogram of time spent eating and drinking each day is highly skewed right. So use this result to explain why a large sample size is needed to construct a confidence interval for the mean time spent eating and drinking each day. So, as we're just told, so the distribution of this time spent eating and drinking each day is not going to be normally distributed since it's highly skewed to the right. So this means the sample size must be large enough so that the distribution of the sample mean will be approximately normal. Okay, so I will just go ahead and write that in. Okay, so I wrote that down and then I also added this in that as the sample size increases, the distribution of t behaves more and more like the standard normal distribution. So remember, we're looking at the distribution of the sample mean, and the sample mean is a point estimate, right? So we are estimating the population mean. So we're using the t-distribution when dealing with problems like this. The t-distribution has a wider spread than the normal distribution, so this can account for that uncertainty introduced when we are estimating these values. Okay, so just keep that in mind. For part B here, we're told there are over 200 million Americans aged 15 or older. We want to explain why this, along with the fact that the data were obtained using a random sample, satisfies the requirements for constructing a confidence interval. So, first of all, we scroll back up here. We're looking at a random sample of 1,001 Americans aged 15 or older. And we're told that the population size is 200 million. So, obviously, the sample size is going to be less than 5% of the population. And then that, along with the fact that the data were obtained using a random sample, will satisfy the requirements for constructing a confidence interval. So all we have to say here is that the sample size, which was 1,001, is less than 5% of the population, which is 200 million. All right. Now for part C, we're actually going to determine and interpret our confidence interval for the mean amount of time Americans or 15 years or older spend eating and drinking each day. Sorry, I realized it'd be much easier if I just pasted the formulas for our lower and upper bound here. So these are our formulas. We're going to have our sample mean minus our critical value, t of alpha over 2, times our sample standard deviation divided by the square root of our sample size for our lower bound. And then for our upper bound, we're just going to add this quantity to our sample mean. Okay, so the first thing that we need to do is find our critical value for t of alpha over 2. So T of alpha over 2 for a 95% confidence interval is going to be given by T of 0.025. We showed that in one of the other examples when we were looking at the critical value for Z of alpha over 2. Now from here, we need to figure out what this actually means, and we can do so with this table here. So for the t-distribution, we're looking at the area in our right tail, and we're going to do so with the degrees of freedom. Now, the degrees of freedom are just going to be n minus 1. So for this example, our degrees of freedom, which I'm going to abbreviate as df, is just going to be our sample size minus 1. So we're going to have 1,000. So what we need to do is look at the degrees of freedom column, find our n minus 1, which is 1,000, and then look at the area here in our right tail given by this alpha over 2 value. So in this case, it's going to be 0.025. So going back to this table, we're going to look at this column for 0.025 and then this row for 1,000. Doing so, oh, sorry, this column for 0.025 and then the row for 1,000. Doing so, we're going to get that this critical value is 1.962. So this gives us 1.962. And now we can plug everything into our lower and upper bounds. So for our lower bound, we're going to have our sample mean, which is given by 1.22 hours. And then just for reference, our sample standard deviation is given by 0.65. We're going to plug both of those into this formula. Plugging this directly into a calculator here, we're going to get 1.180. Now for our upper bound, we're going to have 1.22 plus this product of our critical value times our sample standard deviation divided by our sample size. Plugging that directly into a calculator, we're going to get 1.260. So this means we are 95% confident that the mean amount of time Americans aged 15 years or older spend eating or drinking each day is going to be in between 1.180 hours and 1.260 hours. Okay, so I'll just write a blurb in right there. Okay, so I just wrote that interpretation of this confidence interval in here. And then lastly, for part D, could the interval be used to estimate the mean amount of time a 9-year-old American spends eating and drinking each day? And the answer is no. The sample that we looked at was Americans 15 years or older. A 9-year-old American is a member of a different population. So no. We'll just say a 9-year-old American is a member of a different population. Okay, so for this problem, this doctor wants to estimate the mean serum HDL cholesterol of all 20 to 29-year-old males. And we want to determine how many subjects are needed with 1.5 points with a 90% confidence, assuming that our standard deviation is 12.5. What happens if this doctor would prefer a 95% confidence? How does the increase in confidence affect the sample size required? So we're going to use this formula to find the sample size required to estimate the population mean. That's what we're doing here. So this is going to be our critical value, z of alpha over 2, times our standard deviation divided by our margin of error here. And then we're squaring this. Okay. So for 90% confidence, we're just going to plug this information directly into this formula. In a 90% confidence interval, our critical value z of alpha over 2 is going to be 1.645. We showed how to find that in the last couple examples. We'll multiply this by the given 12.5, and then our margin of error is going to be 1.5. Looking at this within 1.5 points. Plugging this into a calculator, this is going to give us 188. And then for 95% confidence, we're going to do the same exact thing, except in this case, if we're looking at 95% confidence, our critical value z of alpha over 2 is going to be 1.96. So that's the only thing that is changing here in this formula. This is going to give us 267. So clearly there's a pretty big jump here from going from 90 to 95%. So increasing the confidence level increases the sample size needed. So increasing the confidence increases the sample size needed. So for the last question in this video, we're looking at question 16 from section 9.3. We're told that in a random sample of 40 visitors to a certain theme park, it was determined that the mean amount of money spent per person at the park was $93.43 per day, with a standard deviation of $15. So we're going to construct and interpret a 99% confidence interval for the mean amount of time spent daily per person, or sorry, the mean amount of money spent daily per person at the theme park. So in this case, we're going to construct a t-interval, and I'll kind of list the reasons why here, but we are estimating the population mean. We don't know the population standard deviation. We're just given the sample standard deviation, and this population is normally distributed. So I'll list those reasons here, and then I'll paste the formulas for the lower and upper bound for our t-interval. So next we need to find our critical values, t of alpha over 2. So in this case, we're looking at a 99% confidence interval. So this means our alpha is going to be 0.01. So with this information, our critical value, t of alpha over 2, is going to be t of 0.01 over 2, which is t of 0.005. Now from this table, actually, if we scroll up, if you look at this table in our appendix, we're able to figure out what that critical value is. So in this example, our degree of freedom is going to be 39 since our sample size is 40. And then we're just going to look at that row corresponding to 0.05. Doing so, we're going to get that t of 0.005 is 2.708. And this is for 39 degrees of freedom. Okay, so with this information, we can plug this directly into the formulas for our lower and upper bound. So for our lower bound, we're going to have our sample mean was 93.43. We're going to subtract out our critical value times our standard deviation, divided by the square root of our sample size, so 40. Plugging this directly into our calculator here, we're going to get 87.007. And then doing this for our upper bound, but instead we're going to be adding this quantity. Plugging that into a calculator, we're going to get 99.853. Okay, so this means we can be 99% confident that the true mean amount spent daily per person at this theme park is between $87 and $99. So we're 99% confident the mean amount spent daily per person at this theme park is between this amount and this amount. All right, so that's how we would construct a t-interval here to estimate our population mean.